Another characteristic of conic sections that you should be aware of is what is called eccentricity. Like you maybe even heard the word like eccentric, like, oh, this math teacher is so eccentric, right? He's so excited. And the more eccentric, I guess the more extreme your shape is. So if you think about an ellipse, the more stretched it is, it's actually going to have a higher value of eccentricity. The more circular it is, it's going to be lower. And in fact, a circle is very plain. And so we're going to find out that a circle's eccentricity is actually going to be equal to 0. It has no eccentricity. But we're going to define eccentricity as the ratio of C to A. And C is a distance, and I think distance, so we're going to think positive. I know we usually do a plus or minus for direction, but positive distance. So C is the distance to the focal point, and A is half of the major axes, so from the center to the end point of one of the major axes. And again, it's a distance, so we're going to think of it as the positive. Even though when I graph it, I'm doing plus and a minus on either side. Okay, and that's it. That's just the ratio, C to A. So we can look here in example 3. I can pick off my A value right away because I know that this value represents A squared, right, larger than that. So I know right away that my A value is equal to 6. And then to get the C value, I would just have to remember C squared is A squared minus B squared. C squared equals 36 minus 14. Oh, I was so nice to you. So C squared is equal to 25. C, normally I think about it is root 25, which is 5, is a plus minus. But since it's just a ratio of distances, I think of just the positive value I need. So my eccentricity, I'll call it capital E, not to confuse with the lowercase exponential number. E is equal to C over A, which is equal to 5 over 6. Okay? Now, since your focal length is always going to be inside the ellipse, which means it's going to be less than your A value, your ratio for an ellipse should always be less than 1. But the closer it is to 1, the more stretched it's going to be. And again, the closer it is to 0, the more circular it's going to be. Okay? And it's kind of just like a descriptor. Helps you describe the curvature of that ellipse. So now example 4 says, find the eccentricity in each of the ellipses in example 2. So I re-brought them down here. So this was example 2. And if you remember from example 2, our A value, I believe, was 5. Is that right? 1, 2, 3, 4, 5. So our A value was 5. And I think we already calculated what the C value was. I want to say it's 4, because I think it's like a 3, 4, 5 triangle here. But let's just double check. Our C value was 4. So then, if that's the case, the ratio of C to A is eccentricity equals 4 to 5. And again, a value that's less than 1. That's like, what, 0.8? How much was this one up here? 5, 6? So like 0.83. So this one's a little bit more eccentric than that one. So this one will feel and look a little bit more stretched. Okay. And then the last one, I want to say our A value was 10. Is that right? Yeah, if A squared is 100, A is 10, and our C value was 2 root 21. So our A value was 10, and our C value was 2 root 21. And again, I know this number is less than 1, because if you think about them from a squared point of view, 10 is root 100, and 2 root 21 we knew was root 84. So I know that this value is smaller than that value. But when I express it C to A to give my eccentricity, although it's a terrible C, then I still want to do 2 root 21 over 10, which reduces to root 21 over 5. Okay, so that's my eccentric value. Okay, very good.